So today we're talking about decision trees, and these are one of the most intuitive and easy to explain algorithms available to us. And the reason for this is because we use them so often in our daily life. So think about going to a hospital, for instance. So you're not feeling good. You think you have high temperature and you go to the hospital. Okay. And then a doctor might check your temperature. So he or she might use a thermometer to check your temperature, and the temperature, if it's more than a certain threshold, right, if it's more than a certain threshold, then you're admitted. So you're admitted immediately into the hospital. You might get a drip, and so on. And this is how the things are managed, right? On the other hand, if you don't have high temperature, the doctor might ask you to just relax at home. So you might just go back home and uh, and just rest over there and wait for yourself to recover. Yeah. Now now this whole process is a decision tree, right? So you had a certain temperature. So let's represent it here. So you had a certain temperature, and if this temperature was higher than a certain threshold, so if this was greater than a threshold, the doctor said, yes, you should be admitted into the hospital. If it was lower than the threshold, lower than equal to the to the threshold which the doctor decides, right? Then you just rest at home. So this is a decision tree, and you can see that it's in the form of a tree. I mean, you have the root node, which is the node here, which is that's the root, and these are the so-called leaves. These are the leaves of your tree, and both of these nodes are leaves. And the reason they are leaves is because they don't have any children. And then once you have this, you can also represent it using a plot. So on the x-axis, along the x-axis, we can have the temperature, yeah, and on the y-axis we have admit or don't admit, right? So if you admit to a hospital, then we can assign a value of 1, otherwise it's a value of 0. So if the temperature was higher than a certain so the temperature was higher than a certain threshold, right? This is your threshold. If it's higher than a certain threshold, then you admit the patient. So the value of admit is 1 beyond a certain threshold, and lower than this threshold. If you're below this threshold, then you don't admit the patient. So the value is 0. So you can think of it as a classification problem that only uses one feature, and that feature is temperature. Okay, and it can get more complex than this. So let's say instead of one feature, you also have so instead of just the temperature, you also have stomach pain as a feature. So along the y-axis, you can have stomach pain. Okay, and only if the stomach pain and the temperature are above a certain threshold, right, that's when you admit someone. So in this region, you will be admitted, because in this case your stomach pain is higher than a certain threshold and your temperature is higher than some other threshold. Okay, so this is the critical region where you'll be admitted. Here on the other hand, right, if you look at this region here, you'll just be requested to stay at home and recover from your illness. So this is a two-dimensional case. Then again, this is classification. So here you have a value of 1, and here you would have a value of 0. That would represent that you were not admitted to the hospital, right? You can also do the same for regression. So in case of regression, instead of having a value of 1 or 0, you'll have a continuous variable that predicts the output. But the general setup is as follows. So let's assume that we have a two-dimensional feature space. So we have x1 and then we have x2, and the general setup is as follows. So what you would have, you would divide this whole region, this two-dimensional region, into subregions, right? And each of these subregions would be a rectangle. So let's say obviously for simplicity, you could use more complex shapes, but that just makes the problem incredibly hard. So you would rather have rectangles. So let's say you have one rectangle here, then the next one, I'll use different colors, might be this one, then the other one might be this one, the fourth one might be this, And then you might also have something like this. Yeah. So in this case, you divided the region into five different rectangles. Okay, let's call them R1, R2, R3, R4, and R5. This is how you would usually see the regions being represented also in the literature. So once you have this splitting of the feature space, and I'll discuss how you create this splitting. Then to construct the approximation is quite straightforward. So let's say you're given a test point X. First you will try to find in which region. Find the region where this test point belongs. Okay, so first you'll try to find the region where the test point belongs. Let's assume that X belongs to R3. So X is in R3. So that's where X lies. Then you check which of the training points are in R3. Okay, so let's say we have 4 training points inside R3. So 1, 2, 3, 4. Okay, and then we have the last step, right? So the last step is to approximate. Or to generate an approximation for the label of X, this input X. And the approximation takes two forms depending upon which type of problem we have. In case of classification, we take a majority vote. So you just check which label has the highest majority, and that's the label for your test point. And in case of regression, we just take the mean. Okay, so f of x, which is the model or the model output at point x, would just be the average of all the labels of these 4 points. So y1 plus y2 plus y3 plus y4 divided by 4. Okay, so you just take the average. That's how simple it is. But the question is, the important question really is how to compute these regions. And this is what I will discuss next. So while choosing these regions, one thing should be clear to us, that we want to minimize some loss function over the training data set. Right? This is what we do with every learning algorithm, and this is what we will do with trees also. Okay, and let's restrict ourselves to regression for simplicity. So what we want to minimize is the loss function. So let's first consider the loss function. Okay, so you have a summation over all the points which are in a certain region. So let's call it Rj. I take this point and I subtract from it the approximation at this point, which is f of xi, and I square it up. So I'm using the mean squared error. I also need to sum over all the different regions. So let's say I have j regions, so I need to sum up over all the different regions. So that's the mean squared error which I would like to minimize. So I would like to find regions such that this whole thing is minimized, but this turns out to be an extremely hard problem. Right? So you cannot feasibly solve this. So we need to simplify this. And the way the simplification works is via a so-called top to bottom approach. So top to bottom in the sense that you start with the whole domain and you start splitting it in steps. So you don't try to find these regions in one step, you rather proceed in steps, and you start with the biggest possible domain that you have, and then you start splitting it. So here are the steps involved. Okay, so first, again, we take a two-dimensional input space because that's the easiest to draw. So you start with the whole domain. Okay, and then you choose certain points at which you can make at points at which you can cut this domain. So there are, let's say we take 10 points along x1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you might have, I took too many. So let's say we have 3 points along x2. Usually it will be the same. It will be the same number of points along x1 and x2. So then what you would do is you will first split the domain along this along x1. So let's say we split it along x1, and then once we've done this, when we've split it along x1, we'll compute the error. So now compute the loss function. Okay, and since this loss function corresponds to, and that's just the mean squared error, what we saw in the previous discussion. And let's call this loss function L1 because this corresponds to the first split. And then you will split here, and you'll again compute the loss function. See, when you will split here, right, you wouldn't consider this split anymore. Okay, so this split will be gotten rid of. Then we will have L2 and so on. So along x1 you will have 10 values of L, and along x2 you will have another 3 values of L. So in total you will have L1 to L13, and then you just choose the split corresponding to which the loss is the minimum. So it's that simple, right? So you've tried out all the different splits. Let me repeat this again. You've tried out all the different splits. You split it along along x1, along x1 again, along x1 again. You do it 10 times. You compute the loss function, and you do the same procedure along x2. You compute the different loss functions, and you choose the split corresponding to which the loss function is minimized. Okay, so that's the whole procedure. And then once you have the split at the first step, you do the same for all the different regions. What I mean is as follows. So let's take our domain again, and let's say our split was here. Okay, so we realize this is the split that gives us the minimum loss. Okay, then you would run this whole computation for these two regions separately. So you will run this computation for this region, and then the same computation for this region, and this will provide you with the next split. So this next split could be here, okay, and then the next one could be here. The next one after that could be here, and this is how you keep on progressing in steps, right? Dividing each region you found in steps, and then eventually this leads you to a value of R1 and R2. This eventually provides you with the different regions which help you construct the tree. So this procedure is fine. But what happens if we just let it run without stopping it? So let's consider the following example. We have two input features, x1 and x2, and we have 4 data points. Okay, these 4 data points, and we would like to split the region. We would like to split this input feature space such that the mean squared error is minimized. And the best case scenario for which the mean squared error would be 0 would be that each of these training points belong to one and only one region. So for this case, the split might look as follows. We might have one split here, and then the last one here. So you can see that each of the training points belong to only one region, and in this case the mean squared error would be 0. Now from a mean squared error minimization perspective, this is an amazing tree, right? But it will not generalize well. So if I give it a new test point, which probably lies here, so if this is a test point at which I want to have an approximation, then the error at this test point will most likely be way higher than acceptable. So we are overfitting the training data set, and by doing that we'll have high generalization error. Okay, so if we now plot this in the splitting in form of a tree, the tree would look something like this. So you'll first have one node, then you have two nodes which result from this split, and then each of these two regions are splitted again. So we'll have 2 additional leaf nodes. So in total we'll have 4 nodes, and each of these leaf nodes will contain one and only one training data point. So the four training data points would belong to each of these leaf nodes. Now as we discussed, I mean this leads to a mean squared error of 0 on the training data set, but that's undesirable because we have high generalization error. So what we need to do is somehow reduce the complexity of this tree. So we need to come up with a simpler model, and by doing that we would sacrifice some amount of training error. So the mean squared error on the training points will not be 0, but then the generalization error would be much better. Okay, so what do we mean by simplifying this tree? That means we would try to give up some of the splits that we performed. So we might remove this split, and when we remove this split, the mean squared error won't be 0, but we might perform well on this testing data point. Okay, so the question is, how do we do this? How do we extract from this tree a subtree, okay, which has a better generalization error? Okay, So if you recall, a subtree basically means either this tree, or this is a possible subtree, then this tree here is a possible subtree, or this tree here is a possible subtree. So there are many different possibilities, and each of these possibilities correspond to removing one of these splits that we have performed here. So how do we extract this subtree that has a better generalization error than this entire tree that I would denote by T? Okay, so we want to find something like T tilde, which is contained inside T, but has a better performance on the testing data set. Okay, so one way to do this is to consider all possible subtrees. Okay, so first idea is to consider all possible subtrees. Now as you can see, for this example, the number of subtrees are quite limited. So one could still perform this operation and come up with a subtree that has a better generalization error. But usually in practice, these trees could grow very deep. Okay, so checking for each of the subtrees would usually not work. And therefore we need a better strategy, we need a smarter strategy to extract different subtrees in a more efficient fashion, so that we're not comparing all the different subtrees, and then from the different subtrees that we have extracted, we choose the one that has the minimum generalization error. And this is what is done via cost complexity pruning. Okay, so this is the idea that I will be discussing next. So this is how the cost complexity pruning algorithm works. Okay, so let's say you have a training data set, which is shown here, and then you have along with it a validation set, which is not used during training. And on the training set, first what you would do is minimize the mean squared error and construct your full decision tree. In the previous example, this full decision tree had 3 levels with 4 leaf nodes. So I'll just repeat it here. Okay, so you'll have we had this tree we have this full tree from the previous example, and this full tree had a mean squared error of 0 on the training set. So the next step is to define a metric. Okay, so this metric helps us extract different subtrees from this full tree. So this is a full tree which we denoted by T, and we would like to extract different subtrees from this full tree. So once we do this, I will discuss what this metric looks like later on, but what you do is you check for different values of the metric, and you extract different subtrees. Let's call it T1, T2 up to Tn. So let's say you extract n different subtrees. Then for each of these subtrees, you compute the mean squared error on the validation set. This was the holdout set given here, and this holdout set was not used while constructing the full tree. And then once you've done this, you extract the tree, you extract the subtree that had the minimum possible error on the validation set. Okay, so this subtree could be this one, Tn. So this would be the output of the algorithm. So the output of the algorithm would be Tn, which would be the subtree that has the minimum possible generalization error. So now let's go back to this metric that I discussed earlier. How does this metric look like, and how do we actually define these different subtrees? So the metric has 2 parts. One is the mean squared error, which is computed on the training data set, plus a penalty term that penalizes the complexity of the tree. So the penalty term looks as follows. You have a penalty parameter alpha and the number of nodes multiplied by the number of nodes of the subtree that we are extracting. Okay, so not only do we want to minimize the mean squared error, we also want to keep the complexity low, because if we extract a highly complex subtree, most likely the generalization error won't be good, which was actually the problem to begin with. So the reason we were doing cost complexity pruning is because the full tree had bad generalization properties. So if we don't penalize the complexity here, we will end up with the same full tree. And this is easy to see if you set alpha equal to 0. So when alpha is equal to 0, we are asking for a subtree that minimizes the mean squared error. Okay, and this is nothing but, this subtree would be nothing but t itself. So this would be the full tree in this case. Okay, and when you set alpha to be very large, so if alpha is set to be very, very large, then the resulting subtree would be extremely small, because we are putting a lot of weight on the complexity of the tree. Okay, so one example in this case might be the root node of the full tree. So if you set alpha to be very large, you might just end up with the root node, and this corresponds to no splitting at all. Okay, so these are the two extremes, and then somewhere in between these two values lies the optimal value of alpha and the corresponding subtree that has the minimum possible generalization error. So this is the intention behind introducing this additional penalty that penalizes the complexity of the subtree we are extracting. Okay, so this brings us towards the end of our discussion. I'll wrap up the video with a few advantages and disadvantages of using a decision tree. So here are a few advantages. So firstly, it's very easy to explain to other people. So easy to explain. Explainability is an advantage of decision trees. So you make these splits along the feature space, and using these splits you can draw a tree, and using the diagram you can easily explain why certain decisions are made or why certain outputs are produced by the decision tree. Secondly, people believe that these decision trees mimic human decision making, and this is something we also discussed in the beginning of the video. Now let's discuss a few cons. So firstly, accuracy of these decision trees could be low compared to other regression methods. Even compared to linear regression, it might happen that a decision tree does not provide good enough accuracy. So accuracy would be low. And secondly, the trees that we obtain, right, are very sensitive to initial data. So if you perturb the initial data just slightly, right, the splitting that we have here of the input feature space can change drastically, and this might result in a totally different tree, which will have eventually a different output. So the whole process, the whole algorithm is very sensitive to input data. Slight perturbations can change the output drastically, but there are still techniques to fix this second problem, and I will discuss this in one of my next videos.